Today we'll talk about what I call cliff running projectile problems, where something goes horizontally off a ledge that's up in the air somewhere. As a quick refresher, let's try this problem. Rock A is dropped from the top of a cliff at the same instant that rock B is thrown horizontally. Look at the figure to the right. Notice that the origin has been picked to be below the rock at the start, with y plus y being upward and plus x being rightward. And you're asked what if anything is wrong with these graphs, and then be ready to explain why. All right, so let's look at what the graphs are implying. Here, this says that rock A has some horizontal velocity at the start, but we know that it's simply dropped. It only goes straight down. So we know that that's wrong. It should have no horizontal velocity at the start. And that zero horizontal velocity should stay zero, so actually it should be along the axis like this. On the other hand, it says here that it also has some vertical velocity at the start, and we know that's not true. It's simply dropped. So what is drawn would have been a thing that was thrown like this, but in fact it's simply dropped. So it should start with zero vertical velocity, and then that should go down at a constant rate with a slope of minus g. If we look over at rock B says that it starts off with no horizontal velocity, and then stays that way, which ironically is what A should have been. But B should have started off with some velocity and then stayed constant, which means that A and B on the horizontal were swapped. And then for the vertical, it says that it starts with no vertical velocity, which is true, and then descends at constant rate. So that one is correct. And again, a slope of minus g. All right, projectile motion is just a special case of constant acceleration, wherein we know that the components of the acceleration. In the reference frame we just had, it would be ax is 0 and ay is minus g. The constant acceleration equations apply separately to the horizontal and vertical motion. They both apply, and they apply separately. There's no mixing of the two, except through the time, essentially, which is the same for both. So we can take our earlier things like x equals xi plus vi times t plus half at squared and so on, and write them separately for the horizontal and vertical motion, and put in the thing we just talked about, and we get the equations that are here on the board. The x equations are simpler because, of course, ax is 0, so a lot of terms cancel out. These terms have an acceleration in them. They go to 0 in the other case. That makes these almost trivial, but still worthwhile. Let's see how this plays out. A ball is kicked horizontally off a cliff that is 12 meters high with a speed of 15 meters per second. How long is it in the air before it hits the ground? How far from the base of the cliff does it land? As always, we should start problems by drawing pictures, so I recopied the picture over here, and we set up our coordinate system and named our quantities. So my coordinate system, I'm going to put the origin directly below the ball, but on the ground. In general, if you don't have a better reason, the optimal reference frame is almost always the leftmost, lowest most point, because then all your coordinates stay positive, and you don't have to deal with any of the weird negativity that comes out when geometry interacts with negatives. If you have other reasons, if there's some reason in the problem that makes it sense to do somewhere else, feel free to. You're open to it. The universe doesn't care what you use, but this will often be the convenient one to use. In this system, we know that we start at t equals 0, and we hit the ground at t equals tf. We start at a position of 0 horizontally, because I'm setting my origin directly below the ball at the start, and I'm going to say it lands at a place that I'm going to call R. I don't know R, I don't know TF, that's what I'm looking for. Also, of course, it starts at a height of 12 and it ends at 0. Right? That's a little unusual for us. We usually have been putting the origin right at the start of the object, but here it's convenient to actually have the object start with some height and come down. The time in the air is often called the time of flight. That's what the F means in TF. It's symbolized by TF. The horizontal distance by a projectile is traditionally called its range, and we usually symbolize it with capital R. Plugging all those things in, at the moment it's about to hit the ground, at the time of flight, then we get this, that its final velocity in the x is 15, just like it was the whole way throughout, and its final velocity in the y is minus g times however long it's been in the air. The range is 15 meters per second times the time it's been in the air. It ends at 0, starts at 12, and then gains at minus a half gt squared. And likewise for the vf square equation. The things in blue are the values that we don't know, but that we want. And the things in orange are the values that we don't know and we don't care about. Not that they're bad, but we don't have to find them. If we find them along the way, that's great, but it is important. Most importantly, notice that there is one equation where TF appears alone with no other unknowns, meaning we can solve that. and we will. 0 equals 12 meters minus a half GTF square. Bring a half GTF squared to the other side. Cross multiply by 2 over g, so that TF squared is 2 times 12 meters over 9.8 meters per second square, which apparently comes out to be 2.448 seconds squared. I have this trapped in a square, so I square root it so as to free the t square. That means I square root the other side. And I remember that whenever I take a square root, this is a positive number, and I put a plus and minus to capture that there are two answers to that. There are two numbers whose square is 2.448. Plus 1.56, but also minus 1.56. Of course, the time of flight can't be negative. The ball can't land before it's launched. So we would cross out that, and we'd say that t equals minus 1.56 seconds is unphysical. And you're allowed to just put a line through it and say unphysical. It doesn't match the situation we've set up. So the actual time of flight must be 1.56 seconds. Now we can go back and put that in our equations. VF remains 15 meters per second. Nothing's going to change that. VFY we could compute. It's minus g times 1.56, but I don't care about VFY, so I'm not going to. Here's where it gets paid off. The range is 15 meters per second times 1.56. This equation gives us our range. We can now say that r is 23.4 meters. That's often going to be the thing where we find the range and get the time, or find the time and get the range. Isn't guaranteed, isn't necessary, but is the most common kind of problem that shows up. All right. Do this one as a practice, and then we'll move on to the next slide, which will show the solution. Moving at 2.8 meters per second, Alice runs horizontally off a cliff that overlooks a lake 4.3 meters below. How many meters from the base of the cliff does she land in the lake? So pause the video, take a shot at it, come back, and we'll solve it. The first thing would be, of course, to draw the picture and add in our important things like our axes. So this is the thing. This is Alice running off. And what do we know? Well, let's put our origin and axis here, just like before. In which case, we know that Alice starts at 0 at the initial time of 0. Of course, she also starts at a height of 4.3 meters. And then eventually Alice reaches the water. We hope. I guess we should make this water so she's not in trouble. Where x is some range, t is the time of flight, and y is 0. During that entire motion, she's accelerating downward with magnitude g, and we were told that this height, well, I guess we've already said, is 4.3 meters. So then we would take the equations and plug in. It would look something like this. That VFX is still VIX always, and then we have that this is true. These are equations we're plugging into, right? True at any time. These are true at any time. At the time we have, this will be TF. So when we plug into it there, we'll have the TF equation like before. 0 is 4.3 minus a half GTF square. Here we get TF is plus or minus 0.0936. That's the only physical meaning. The positive one is the only physical meaningful one. Takes about 0.93 seconds for her to hit the ground, and so her range is 2.6 meters. Different one to try. A marble is fired horizontally off a table from a height of 2 meters. It lands 2.64 meters from the base of the table. What was the marble's speed when it was launched? So this is a very different kind of thing. We again should draw our picture, so take a few seconds to do that, and then I'll catch up. Marble starts here and lands here. We know this height is 2 even, and we know that this distance is 2.64 meters. So let's take a reference frame as we've been doing, in which case we know that at t equals 0, x equals 0, and y equals 2. And at t equals tf, x equals 2.64, and y equals 0. But what we're missing on the picture so far is we also have some velocity, and we'll say v initial x is some number that we're looking for. It's the thing we want. With a little bit less messiness in handwriting, it looks something like this. Notice we do know that VIY is 0. It's launched horizontally. All right, so we go back to our equations and we see which of them apply. we still have this equation that we've been doing involving yf's, because we still have a lot of information about the vertical motion. So we can still find the time of flight, because remember the time of flight doesn't depend on the speed. So I can know how long it was in the air. And it turns out that's about 0.63 seconds, 0.64 seconds, I guess. Again, we only take the positive root, even though we get both of these. And we say, well, but the distance it travels is the initial speed times the time. I know how far it traveled, which is 2.64 meters. I know how long it took, which was this. So the initial speed must have been 4.13 meters per second. Right? And they basically, these are the two kinds of problems that are easy to imagine might be asked. These are the kinds of things that could be asked.